In this video, we're going to learn about logical equivalences in propositional calculus. So here's some motivation for that. We've got two well-formed formulas here. The first one is P and Q, and the second one is Q and P. Now those are two different well-formed formulas because a well-formed formula is just a collection of our logical symbols, and those are different collections of logical symbols. But they have a special logical property, which is that they always have the same truth value, in the sense that if you have any truth assignment whatsoever on the variables P and Q, then the truth value of P and Q is the same as the truth value of Q and P. So they're not the same formula, but they always have the same logical value. Secondly, you'll often see in texts other than the lecture notes for Math 5, expressions like this, so P and Q and R. And you know that that is not a well-formed formula, so it would need more brackets to be a well-formed formula. For example, P and Q and R is a well-formed formula, as is P and Q and R. So how is it that people write things like this and give them logical meaning even though they're not well-formed formulas? And the answer is that you've got two different ways in which you could make this into a well-formed formula by adding some brackets. And while they don't give equal well-formed formulas, so the two well-formed formulas I just wrote down are not the same, they are logically equivalent, and that means that they have the same truth value under every truth assignment on P and Q and R. And these can be useful in two different ways then. The idea of logical equivalence can be useful because first, I'm looking at point 2 that I've written here, it allows us to be a little less pedantic about brackets. We can be more relaxed and write things like P and Q and R, knowing that they're not well-formed formulas, but actually if you turn them into a well-formed formula by adding some brackets, then no matter how you do it, you get something which is logically equivalent. And the other reason is that we're often looking at proving mathematical statements which are given to us in some complicated logical form. Now if you have two logically equivalent well-formed formulas and you want to prove that one of them is true, it's equivalent to prove that anything logically equivalent to it is true, because you know that these two well-formed formulas are logically equivalent, so they always have the same truth value. And that's useful because it allows us to manipulate logical statements we're trying to prove until they have a form which is actually easier to work with, or perhaps simpler or easier to understand. So let's move on to the definition of a logical equivalence. The definition here is that two well-formed formulas, phi and psi, are logically equivalent, in which case we use this notation with what looks like an equal sign except 3 lines, if and only if they have the same truth value under every truth assignment. So let's look at a really simple example of two logically equivalent well-formed formulas. So my first example here is this one, where I claim P or Q is logically equivalent to Q or P. So how might we prove this then? We have to show that for every truth assignment on the variables P and Q, those two well-formed formulas get the same truth value. So the simplest way to do this for a simple well-formed formulas like this would just be to draw a truth table for both of the well-formed formulas. So we'll have a column P and Q, and we're going to, for P and for Q, and we'll write down all the possible truth assignments that P and Q might have. So we might make them both true, we might make P, Q, and P true and Q false, we might make P false and Q true, and we might make them both false. And we're going to check that under those truth assignments, which are all the possible truth assignments for P and Q, the two well-formed formulas P or Q and Q or P get the same truth value. So let's look at those. Let's write them down as columns in our extended truth table. So P or there we go, P or Q and Q or P. So we'll see what happens when we work out the truth values of these well-formed formulas. So P or Q, P in the first row, P and Q are both true. So what I've got here is true or true, and you know that that is true. And for Q or P, I've got true or true, which is true. Okay, so next, looking at the next line, when P is true and Q is false, then here I get true or false, which is true, and here I get false or true, which is true. Third line, I have P false and Q true, so here I've got false or true, which, looking at the truth table for or, is true, and here I'll get true or false, which is true. And finally, on the last line, I've got false or false both times, and that is false. So what you get from the truth table is the following. You get that these two well-formed formulas had the same truth value under every truth assignment, and that means they're logically equivalent. Okay, so our table allowed us to summarize all of the possible truth assignments on the two variables P and Q, and we've checked that under every one of those truth assignments, the two well-formed formulas, P or Q and Q or P, got the same truth value. So let's look at another example now where we want to show that two things are not logically equivalent. So P or Q and P and Q. So, I mean, if you just think about the meaning of these things, it's pretty clear they're not going to be logically equivalent. There are obviously cases where one will be true and the other is false. But I want to illustrate how we prove that two formulas are not logically equivalent. And the way we do this is that we must give a truth assignment for which those two well-formed formulas get different truth values. So let's write that down because it's so important. To prove this, we give a truth assignment let's call it alpha, for which alpha of P or Q, forgive me for dropping the brackets, is not the same as alpha of P and Q. And of course, if you take, for example, if we take alpha of P to be true and alpha of Q to be false, then P or Q would be true, but P and Q would be false. So this would give an example of a truth assignment that gave different truth values to those two well-formed formulas, so they are not logically equivalent. Okay, let's look now at some more interesting examples of logical equivalence and some more useful examples of logical equivalences. So the first two in my theorem, it says that if you've got any three well-formed formulas, phi and psi and theta, then the first logical equivalence is that phi and psi is logically equivalent to psi and phi. So this is just like the thing we already proved. Similarly, part two, phi or psi is equivalent to psi or phi. So those are called commutativity laws. Commutativity is saying that the order doesn't matter. So this is saying that up to logical equivalence, the order in an and well-formed formula or an or well-formed formula doesn't matter. And perhaps the more interesting ones are number 3 and number 4, which are called associativity rules. And those say that, first of all, phi and, in brackets, psi and theta, is logically equivalent to phi and psi, in brackets, and theta. So really what that's saying is that if you take a formula, not a well-formed formula, but a formula like phi and psi and theta, well, it's not a well-formed formula, but there are only 2 ways to put brackets in so that it is. And part 3 is telling you that the 2 ways to put the brackets in give you logically equivalent well-formed formulas. And that means it's actually safe to write down expressions like this and just to interpret that expression as being some way, one of the 2 ways of putting brackets into it to make it into a well-formed formula. Okay, so part 4 then says the same thing for or. The or is associative in the same sense. So, I don't know why my eraser is not malfunctioning, but it is. Okay, let's prove one of these things. Let's just prove one of them, namely number 3. In fact, I'm not even going to do the whole proof. I'm going to show you how to go about proving these. And what we should do is simply look at all the possible cases. So to prove that 2 things are logically equivalent, you have to prove that under any truth assignment they get the same truth value. So we're going to draw a table, and let's call this proof of part 3, and we're going to draw a table which summarizes what can happen under any truth assignment for the variables involved in these well-formed formulas. So I'm going to have a column for the well-formed formula phi, a column for psi, and a column for theta. And any truth assignment will make these things either true or false. So under any truth assignment whatsoever, we either have them all being true, or, well, the 7 other combinations. So it could be like this, or it could be like this, okay, or it could be like this, okay, or it could be right, and so on. There are 8 different combinations in total. So we have to think about all of the 8 different possibilities, and we're going to think in each of those 8 different possibilities, what are the truth values which the 2 well-formed formulas in part 3 will get. So the 2 well-formed formulas are phi and psi and theta, and phi and psi and theta. So let's work out just these first couple of rows. So in the first, let's look at the entry which should be going just here. So if I work out this entry, what I have is true and true and true. Okay, true and true is true, so this is true and true, which is true, so that is what goes there. Okay, now let's look at what goes here. So here, let's work it out. Again, we can just do this using the way we know for evaluating well-formed formulas truth values under a truth assignment. So we've made them all true, so what we've got is true and true and true, and again true and true is true, so we've got true and true, which is true again. Okay, so this one is true. Okay, let's do the second row of the truth table. So we'll begin with the thing which is supposed to go here. We'll work this one out. So if I just take a pen here and work this out, what have I got? I've got phi being true, so I've got true and false and true. Now that is true and, well, false and true is false, so this is true and false. So this is false, so I should put a false here. And if we go to the next one, well, we work it out under this truth assignment. Let's look what should go there. So take a different pen there. What happens? I've got true and false and true like this. So this is true and false is false, so false and true, and that of course is false. So here we get a false. Okay, so we can keep doing this, right? We have 6 more computations to do, 12 more computations to do, what you will find is that in every case, the 2 well-formed formulas that label the last 2 columns always have the same truth value, and therefore they are logically equivalent.